Ever get that feeling like, the clock on the wall is ticking at a different speed for you than for the person sitting right next to you?
Yeah, yeah. It sounds a bit out there, doesn't it?
It does, but that little thought experiment, it actually bumps right up against some of the most, well, mind-bending stuff we've been looking into.
Absolutely. We're talking general relativity,
Hmm.
black holes,
Yeah.
the big picture stuff.
Exactly. So today we're going to take a bit of a whirlwind tour through some ideas that'll really make you, question your grip on reality.
Well, but hopefully without needing a PhD in astrophysics to follow along.
That's the plan. We've been digging through some, frankly, pretty dense material, pulling out the bits that really make you go, whoa.
Yeah, finding those key insights.
So our mission, if you will, is to unpack some of the truly wild implications. We're talking about how space and time aren't this fixed background we always assumed.
Uh-huh. How they're more flexible.
Right. And the utterly bonkers physics around black holes, where things get stretched like cosmic spaghetti.
The infamous spaghettification, yes.
And also how the whole darn universe came to be and what it's, well, actually made of, which is surprisingly weird.
It really is. Okay, so where do we start?
Okay, let's dive in. Starting with something that might just make your brain do a little, I don't know, happy glitch. This idea that time isn't universal. It doesn't kick the same for everyone.
It's fascinating, isn't it? This notion that your experience of time, it can actually depend on something as simple as how fast you're moving relative to someone else.
Okay, break that down, like the thought experiments?
Yeah, exactly. Imagine you've got two friends. Let's call them Anya and Ben. Anya's on a super speedy train, right? And Ben's just standing still on the platform watching her go by.
Okay, got it. Speedy train, stationary observer.
Now, they both have these little gadgets that flash a light beam up to a mirror on the ceiling and back down. Bing, bing.
Simple enough.
For Anya, on the train, the light just goes straight up and straight down. Easy. The flashes hit the detector at the same time, simultaneous.
Makes sense from her perspective.
But for Ben, watching from the platform, he sees the light being, but he also sees it moving forward with the train. So the path the light takes isn't straight up and down anymore.
Oh, it's diagonal, right, because the source moved.
Precisely. It travels a longer, slanted path going up and a longer slanted path coming down. Now, here's the kicker. The speed of light is always the same for everyone. For Anya and D for Ben.
That's the fundamental rule, yeah.
So if the light has to travel a longer path from Ben's point of view, but its speed hasn't changed, well, it must take longer, right?
Okay, yeah. Longer path, same speed, takes more time.
Which means for Ben, those light flashes hitting the detector, they don't happen at the same time anymore. What was simultaneous for Anya is not simultaneous for Ben.
Whoa, so just because one is moving relative to the other, their idea of at the same time is different. That's
Yeah,
trippy.
it is. And it's not just a perception thing, it's fundamental. It means observers moving relative to each other literally slice up space-time differently. Their axes of space and time are skewed relative to one another.
Right, it's like if you're trying to throw a ball straight up in the air while you're walking, to you it just goes up and down. Simple.
Mm-hmm.
But to someone watching you walk by, the ball is also moving forward, so its path through the air looks like an arc. Totally different.
Good analogy.
Yeah.
But with light and time, it's baked into the fabric of reality itself.
Mm-hmm.
This difference isn't just about appearances. It means their now is different.
So no universal now. I once missed a train because I swore I had more time. Maybe I was just moving too fast relative to the station clock.
Maybe so. And this whole idea, this non-agreement on simultaneity, it leads directly to other weird consequences, like how velocities add up.
Oh yeah, you mentioned that. It's not just simple addition near light speed.
Nope. In our everyday lives, sure, if a car is going 60 miles per hour and passes one going 50 miles per hour, the difference is 10 miles per hour. Simple subtraction.
Right.
But when you're dealing with speeds close to the speed of light, you can't just add or subtract them like that. There's a special formula, the relativistic velocity addition formula.
And the upshot is,
The upshot is you can never just add velocities to get something faster than light. If you're on a spaceship going zero point 0.9 times the speed of light and you shoot a probe forward at 0.9 times the speed of light relative to you.
you don't get 1.8 times the speed of light.
Exactly. You get something like 0.99 times the speed of light. You get closer and closer, but you never cross that ultimate speed limit. The universe has this built-in governor.
Which is just wild. A cosmic speed limit enforced by the nature of space and time itself. Okay, mine's sufficiently bent on that. Now let's layer on gravity. What happens when gravity gets intense, like near black holes?
Okay. Now we step from special relativity, which deals with constant velocity, into general relativity, which brings in acceleration and gravity.
And gravity isn't really a force. That's the idea.
That's the core concept. Einstein realized gravity is the curvature of spacetime caused by mass and energy. Think of putting a bowling ball on a stretched rubber sheet.
It creates a dip, and marbles rolling nearby curve towards it.
Exactly. The more mass you pack into a smaller space, the deeper the dip, the more space-time curves. And a black hole is where that curvature becomes extreme.
So extreme that light can't escape.
Right. And the boundary where that happens is called the event horizon. It's often called the point of no return, which it is, but it's even weirder than that.
How so?
At the event horizon, according to the math, the roles of space and time seem to, well, flip in a way.
Flip. Space becomes time. What does that even mean?
It means that the direction we normally think of as space, like moving radially inwards towards the center of the black hole, it takes on the characteristic of time.
Okay, hold on. So just like we can only move forward in time, once you cross the event horizon, you can only move inwards towards the center.
That's the implication.
Yeah.
Moving towards the singularity, the center point, becomes as inevitable as moving towards the future is for us out here. You can't stop yourself any more than you can stop time.
So the geometry itself compels you inward. It's like instead of choosing to walk across a room, the room itself is just constantly shrinking around you, forcing you to the middle.
That's a really good way to think about it, yeah. Another analogy some physicists use is that inside the horizon, space itself is falling into the singularity faster than the speed of light.
Space is falling.
Like a waterfall.
Mm.
But the water is the fabric of space. Even if you had a rocket that could travel at the speed of light pointed outwards, the space you're in is collapsing inwards faster. You'd be carried down anyway.
Wow. Okay. That is bizarre. Our intuition just completely breaks down there. You know, sometimes when I'm really late for something important, it feels like time itself is collapsing around me. Maybe it's just a mild case of being near a metaphorical black hole of tardiness.
Huh. I think we've all felt that gravitational pull towards the deadline.
Definitely. Now, what about those wormhole things, Einstein-Rosen bridges? Are those real possibilities coming out of this math? Could they be shortcuts?
Wormholes. They are mathematically permitted by some solutions to Einstein's equations. Yes. The idea is captivating a tunnel connecting distant points in space-time, or maybe even different universes.
Like a cosmic subway.
Wouldn't that be nice? But there's a catch, a big one. The simplest types of these wormholes, the ones described by the Schwarzschild or Kruskal solutions, they aren't traversable. Meaning the throat of the wormhole pinches off or collapses faster than anything, even light, could travel through it. It's like finding a doorway that slams shut the instant you try to step through.
So, mathematically interesting, but practically useless for travel.
In these simple models, yes. Now, people theorize about exotic matter or other complex scenarios that might stabilize a wormhole, but that's highly speculative stuff, not something standard general relativity predicts easily.
Okay, so no interstellar shortcuts just yet.
Got it.
All right, let's pull back from the super weird specifics and look at the whole universe. Cosmology, where did it all come from? What's the big picture?
Right. So our current best understanding is wrapped up in what's called the standard CDM model of cosmology. That's lambda CDM.
Lambda CDM. Okay, what does that tell us?
It paints a pretty surprising picture of the universe's inventory. If you tally up all the energy and matter, the stuff we're made of, ordinary baryonic matter, protons, neutrons, electrons that makes up stars, planets, us,
Yeah. How much is that?
it's only about 5%.
Wait, 5%? That's it.
That's it. About 25% is something called dark matter. We know it's there because we see its gravitational effects, galaxies rotating faster than they should, light bending around clusters. Yeah. But we haven't directly detected a particle of it yet.
Okay, so 5% normal stuff, 25% mysterious dark matter. What's the rest? That's 70%.
That remaining 70% is even more mysterious. Dark energy.
Dark energy. And what does that do?
It seems to be causing the expansion of the universe to accelerate. It has this sort of repulsive gravitational effect, pushing space-time apart. Its nature is one of the biggest puzzles in physics today.
Wow. So 95% of the universe is made of stuff we don't really understand? That's humbling.
It absolutely is. It means everything we see with telescopes, all the stars and galaxies, it's just the tip of the cosmic iceberg. Like trying to understand the ocean by only looking at the foam on the waves.
Incredible. So what's the evidence for this whole picture? The Big Bang and all that?
One of the absolute cornerstone pieces of evidence is the cosmic microwave background, the CMB.
The afterglow of the Big Bang, right?
Exactly. Its light release from the universe was very young, only about 380,000 years old. Before that, it was so hot and dense that it was opaque, like a thick fog.
Uh-huh.
As the universe expanded and cooled, atoms formed and the universe became transparent. The light from that moment has been traveling ever since, stretching out with the expansion of space into the microwave part of the spectrum.
And we can detect it today.
Yes. Penzias and Wilson famously discovered it accidentally in the 60s. It comes from all directions in the sky, incredibly uniform, but with tiny temperature fluctuations. It's like a baby picture of the universe.
A baby picture. I like that. So to track this expansion, scientists use something called the cosmic scale factor, A.
That's right. The scale factor A is basically a way to measure the relative size of the universe over time. We usually set A to be 1 today. If A was 0.5 in the past, it means the universe was half its current size. Distances between galaxies were half what they are now.
Okay, so it tracks the stretching of space.
Exactly. And what's really interesting is how the density of different things changes as A grows.
How so?
Well, think about regular matter. If the universe doubles in size, the volume increases by 8 times, 2 cubed. So the density of matter drops by a factor of 8. It just gets diluted.
Makes sense. More space, same stuff, less dense.
Right. Now, radiation, like the CMB photons, gets diluted by the volume increase, but it also loses energy because its wavelength gets stretched by the expansion. Remember, longer wavelength means lower energy for light.
Ah, so radiation density drops even faster than matter density.
Exactly. It drops as 1 over a to the 4th power, while matter drops as 1 over a cubed.
And dark energy.
That's the weird one. The data suggests dark energy's density stays constant, or very nearly constant. As the universe expands, more dark energy just seems to appear to keep the density the same.
Wait, it doesn't dilute? How?
We don't know. That's part of the mystery. It might be an intrinsic property of space itself, the cosmological constant Einstein originally proposed and then discarded.
So the universe's composition actually changes over time. Like early on, radiation dominated, then matter, and now dark energy is taking over.
Precisely. That changing balance drives the evolution of the universe's expansion rate.
Okay. Now, you mentioned we can only see so far. The cosmological horizon, is that like the event horizon of a black hole?
It's different, but related to the finite speed of light and the age of the universe. Because the universe is about 13.8 billion years old, light from objects farther than about 13.8 billion light years couldn't have reached us yet. But because space itself has been expanding.
The actual edge is further away.
Right. The edge of the observable universe is currently about 46.5 billion light years away. The cosmological horizon is that boundary. We simply can't see anything beyond it because the light hasn't had time to get here since the Big Bang.
So there could be loads more universe out there we just can't see.
Almost certainly. Our observable patch is likely just a tiny fraction of the whole thing, whatever its total size might be. Could even be infinite.
Mind-boggling. Okay, one more piece from the early universe. Inflation, this super fast expansion right at the start.
Yeah, inflation is a theoretical period thought to have happened in the first tiny fraction of a second, like 1036 to 1032 seconds after the Big Bang, an incredibly rapid exponential expansion.
Why do we think that happened?
It solves some key problems with the standard Big Bang model. For instance, why the CMB is so incredibly uniform across the entire sky. Regions that couldn't possibly have exchanged heat or information in the standard model look the same temperature.
How does inflation fix that?
Inflation suggests the entire observable universe we see today originated from a tiny, tiny patch that was causally connected before inflation blew it up to enormous size. It also explains why the universe appears geometrically flat on large scales.
And it created the seeds for galaxies.
That's the idea. Tiny quantum fluctuations present in that initial patch got stretched to cosmological scales during inflation. These tiny density variations then acted as the seeds, gravitationally attracting matter over billions of years to form the galaxies and clusters we see today.
Wow. So a super quick bump at the beginning set the stage for everything.
In a nutshell, yeah. It's a powerful theory, though the exact mechanism is still debated.
It really ties things together. Okay, before we wrap up, our sources also touch on some of the, let's say, mathematical language needed for all this. Things like tensors and covariant vectors. Briefly, why is that necessary?
Ah, yeah, the mathematical machinery. In essence, when you're dealing with curved spacetime and observers moving in different ways, you need a way to write down physical laws so they look the same for everyone, regardless of their coordinate system or state of motion.
Like ensuring the laws of physics don't change just because you're tilted or moving?
Exactly. Covariant and contravariant vectors, and more generally tensors, are mathematical objects designed to transform in specific, predictable ways under changes of coordinates, like the Lorentz transformations in special relativity. The metric tensor, for example, tells us how to measure distances and time intervals in curved spacetime, and it helps raise and lower indices on these vectors and tensors to make sure equations are consistent.
So it's the grammar of space-time geometry.
That's a great way to put it. And things like the Riemann curvature tensor quantify the actual curvature. It tells you how much parallel lines deviate or how vectors change when moved around in curved space. It even breaks down into parts describing how volume changes versus how shapes get distorted, the Riccian wheel parts.
Okay, so it's a precise language for a complex reality. And it all stems from that core idea linking gravity and acceleration, the principle of equivalence.
That's the foundation of general relativity, yes. The idea that locally you can't tell the difference between being in a gravitational field and being in an accelerating frame of reference. That insight leads to things like gravitational redshift light, losing energy as it climbs out of a gravity well.
Amazing how one principle unlocks so much.
Yeah.
Okay, we have covered some seriously deep and, frankly, reality warping territory today.
We definitely have, from simultaneity being relative, to space falling into black holes, to a universe mostly made of mysterious dark stuff.
Yeah. We talked about how time and space are relative, how they can be warped by mass and energy, the truly bizarre physics near event horizons, and this surprising cosmic inventory, mostly dark matter and dark energy, and how the universe evolved.
Key takeaways from grappling with relativity and cosmology.
Absolutely. And considering how drastically our whole perception of something as basic as time changes with motion, and how gravity reshapes geometry, it really makes you wonder, doesn't it?
Wonder what?
Well, what other seemingly fundamental aspects of our reality, things we take for granted, might actually be more fluid or interconnected or just plain different than we currently imagine?
That's the big question, isn't it? Are things like consciousness or the arrow of time itself, are they just surface appearances of something deeper?
Exactly. Maybe our everyday assumptions are just, scratching the surface. It's definitely something to ponder next time you're waiting for a train or just staring up at the night sky.
A good thought to leave with. This dive is really just the start.
For sure. It's the beginning of a much larger and way more mind-bending journey into understanding this universe. Thanks for joining me today.
My pleasure.
And until next time, keep asking those questions, keep exploring. There's still so much out there.